In the second part of this video, I want to make sure that you understand how to do the shoot the monkey demonstration. That's where you have a blowgun aimed at a coconut and a tree. And I told you in class that if you're going to aim want to shoot a coconut out of the tree, as it was falling, you would want to make sure that you aim the dart directly at the coconut. And so let's say your coconut was up here. Now, if there was no gravity, the coconut would just stay there. And your dart would go along this zero gravity path, zero G path. It would go in a nice straight path. Well, with gravity, the coconut falls. But so does the dart. And the dart falls the same amount as the coconut does from the zero gravity path. So this is what I wrote all here in red. Okay? And so therefore, you always want to aim the dart at the coconut. Now let's prove this mathematically for all you AP people out there. It's going to get a little challenging, so just go with me here. Okay? Well, in order to prove this, I got to assume that the distance off the ground of the dart is going to be the same as the distance off the ground of the coconut. So back in last chapter, we said that the distance in the y direction, the distance, was a formula. We had VO plus VOT plus 1/2 AT squared. Okay. Well, if they both got to be the same distance off the ground, I can say the same thing about the distance of the coconut. I'm going to erase this little chart right there. And so I can say the same thing over here, that dy equals DO plus VOT plus 1/2 AT squared. Well, since gravity is the same for both, and they both must hit each other at the same time, the A and T over here are the same thing as the A and T over here. And I forgot to put a square there. And so therefore, these can cancel because the 1/2 AT squares are the same on both sides. Now, the other thing we can cancel out is the dy, because we're assuming, once again, that they are the same off the ground. Well, now we got to prove this. Well, the distance of the dart off the ground at the very, very beginning is going to be 0. So I'm going to put it right here because it's starting on the ground. Now, when the dart goes up in the air, though, we got a sort of a quandary, because the velocity that's given to you is this diagonal velocity here. Okay? Well, this formula requires that we use the velocity in the y direction. See, this is the distance in the y direction. So let's just say the dart's being shot up at an angle of theta. Well, this blue side is going to be the y direction, which is the opposite side. And this red side here is going to be the adjacent side. And so, to get the velocity in the y direction, I'm going to have to use the sine, because whenever you're trying to find the opposite side and you know the hypotenuse, I'm going to use the sine of the angle. So I'm going to put sine of theta times the hypotenuse, which is VO. Now this becomes the velocity in the y direction. Okay? Because this VO is diagonal. This one right here is diagonal. I'm going to bring down my t. Now that equals the distance of the coconut in the y direction. Well, I don't know that, so I'm going to bring this down. It's the original speed of the distance of the coconut in the y direction. But I do know that the original velocity of the coconut, since it was just hanging there, is 0. So now that goes away. Okay, so now I can get rid of this because it's 0. So I've now proven that the distances in the y directions are going to be equal because distance equals velocity times time. But that doesn't mean that they're equal in the x direction. So I got to have something that's going to prove that the x directions also are involved in this. Well, as of right now, time does not have a direction. So I'm going to use this t right here and substitute in for t a formula that has the x direction in it. Well, let's come back here to the old formula of velocity equals distance over time. Well, let's cover up that t And if you notice that t now becomes distance divided by velocity. And we want this in the x direction. Okay? So now I'm going to have, watch this real quick, I'm going to bring down my sine of theta times the diagonal velocity over the velocity in x direction equals, there's no distance here. But I don't know the distance, the velocity in the x direction on the bottom here. So now I have to substitute out for that. Well, think about it. If you're trying to find the adjacent side, this is the same thing as your velocity in the x direction. Okay? I'm now going to substitute in for that. So I'm going to put the sine of theta times the velocity diagonal, or the hypotenuse, times the distance in the x direction, all over. Now watch what I substitute in for here. For Vx, I'm going to put in the cosine, because to find the adjacent side over here, use the cosine of the angle times the hypotenuse. Well, the hypotenuse is VO. And that all equals the distance original in the y direction of the coconut. Let's look what you can do now. VO is on the top, VO is on the bottom, so they go away. So what that tells you is it makes no difference what speed you shoot that dart at, as long as you shoot it at the angle that's given to you between the coconut and the dart. Well, what is sine divided by cosine? Sine divided by cosine here is tangent. So now I have the tangent times distance equals distance in the y direction. Well, let's divide both sides now by dx. What happens to the dx's? They cancel out on this side. And I'm left with dy over dx here. Now, here's how I know that I proved that if I aim the dart at the coconut, I will hit it. dy, you look at the distance in the y direction, isn't that the same thing as the opposite side? And isn't the dx the same thing? Here's your dx down here, okay? Isn't that the same thing as the adjacent side? And what does tangent equal? Opposite over adjacent. So you just proved that if you aim the dart at the same angle as the can or the coconut or whatever you're shooting here, we saw a can in the class, then you always hit it. Let's go down to number 7. Now you have a military jet. So here's your little military jet, or it could be a sock, okay, whatever, it's a little jet. And we want to drop a care package to some terrorists below, because we're good people and we want to help make them better people as well. And so I have a target down here that I want to hit. And I'm going to drop down a little care package to them. And it says that this plane is 9,800 meters above the ground. So they just gave me the distance in the y direction there. They also told me that the plane is flying a speed in the x direction of 200 meters per second. What they want to ask me is how far away. So if you're asked how far, what are you looking for? Distance in the x direction. Does the plane have to be from the target to hit it? Well, if I know distance and I know velocity, I know that distance equals velocity in the x direction times time. Look at this little triangle up here. See, distance, if you cover it up, equals velocity times time. Well, the problem with this is I don't know the time. But if you go back to last chapter, remember how I said physics will never let you forget anything? Time equals the square root of 2d divided by g. Now, this distance is in the y direction because gravity is in the y direction. It's acting downward. Since time has no direction, the time in the y direction has to equal this time over here in the x direction. Okay? So time can be used to go back and forth between directions really, really easily. So now I'm going to put 2 times 9,800 divided by 9.8. Take the square root of that whole thing. And now I get a time of 44.7 seconds. Well, what I'm going to do at that time, since time in the y direction is the same as time in the x, I'm going to put it back in here. And so now I'm going to take my velocity that the jet's going at 200, multiply it by 44.7, and that will end up giving me a total of 0.00498. And let's see here. So it gives you a total decimal point right there. So it gives you a total of 8,940 meters away. So if the plane drops the care package 8,940 meters away, it will hit its target and the plane can turn around and go back. Okay. Now for AP, it now asks for the resultant velocity down here. Okay. This gets a little trickier. Because to get the resultant velocity, I remember the resultant's going to come down here like this, okay? But it's made out of two vectors, one going horizontally and one going vertically, okay? Well, I know the horizontal vector never ever changes. That's going to be the 200, okay? And now I got to figure out how fast is it going vertically in this y direction. And so velocity equals acceleration times time. Remember the old triangle that says A equals V over T? So I'm going to take the acceleration. Well, since the the care package is dropping, that means the acceleration is 9.8. The time was the same thing that we got up here of 44.7 seconds. And that gives you a velocity of 438 meters per second in the y direction. And you got to remember, to get the resultant, it's the Pythagorean theorem, because the resultant is going to be this red line here. So the velocity is going to be equals the square root of a squared plus b squared. So I'm going to put in the square root of 200 squared plus 438 squared. And that gives you the resultant velocity of 481.5 meters per second. But you got to remember, that's not all. Velocity vectors also have angles. So the angle is the inverse tan. Remember, it's opposite over adjacent. Well, your opposite side is going to be your y side, so that's going to be the 438. Here's your opposite side over here, right? Your adjacent side is going to be this 200. So that's about 200. And that ends up equaling, let's see, 438 divided by 200 gives you 2. That is completely wrong. Hold on here. I got to take the inverse tan of that. Inverse tan of that answer. And that gives you 65 degrees. And that is what angle that it will actually be coming down at. Okay?